I said pipeline is durable. It's dumped to disk frequently. And that happens before most steps. Not all steps. Echo steps don't necessarily persist to disk every time. And those records of execution are actually written out to one to two files per step. One XML file. You can actually pull up your Jenkins master, look at the jobs, the pipeline jobs, look for the workflow folder. You see a bunch of little tiny XMLs, 1, 2, 3, 4, 5, 6, 7.xml. Each one of those is what's called a flow node. Think of it as the record of a step execution. There's also a series of little log files in there. The implication here is, or the result of this is, you've got about 4 to 5 disk writes for every step you run. Disk writes matter. That's a limited resource, right? So drilling a little bit more into the execution model, I talked about the CPU and kind of the analogy of the query. Think of it like the query planner for a database. The pipeline code runs in a VM. The normal mode of execution is an interpreted language which keeps in memory a representation of the entire program. That gives you the ability to do things like pause and resume to pick up from a failure, but it's also kind of slow. There's a reason languages like Java are JIT compiled. That's a lot faster. Now, there's a way to do that in pipeline. What you can do is add the non-CPS annotation to functions. And what that says is, this is a function, we don't care if it's durable. We just care about the inputs and the output. Something fails, we'll just run it again. But that's really fast, too. If you're going to do something like sorting a lot of data, I'd recommend doing that all in a script off your master. But if you're going to do a sort, do non-CPS. Makes it 5 to 10 times faster. I'll show you some graphs to that point later. One other point, during execution, you guys may have been familiar with script security, probably in the form of getting those really cryptic error messages because something is not permitted. This is what prevents some random user from walking in and rooting your master. But it does come with some performance overheads. So if you've got blessed code in a shared library, say a global shared library, the global shared libraries are not subject to those sandbox restrictions. If you're running pipeline code that's not taken from SCM, you can mark that as out of sandbox if you trust it. If you've restricted access to that SCM repository. And that's a much faster mode of execution. One other point, steps are run from Groovy, but those are Java, and that's also fast. So the step itself has a lot of flexibility in how it executes, and it can do some things a lot faster. All right, so before I go into specific bottlenecks, I'm going to put up one disclaimer here. Pipeline is not a hammer. What I mean by that is, pipeline, you've got a whole lot of different tools. Think of pipeline here as the laptop that's in the middle, controlling how things work. It's the brains of the operation. It's gluing together a lot of pieces. You don't want to use your laptop to hammer nails. Unless you have a ThinkPad. I guess those would probably be OK. I got to put my shout out there. So use the right tool for the job. So for you can do just about anything in pipeline because it's a Turing-complete language, but there's sometimes better ways to do things. So for example, if you're going to do like a complex set of build logic, there's a reason things like Gradle and Maven exist. There's a reason each language generally has an idiomatic build tool. Those are usually a very terse way of doing things, and they're easy to work with. Don't try to use pipeline logic to do things that there's something else better for. Similarly, interacting with APIs is something that I see a lot of in pipeline code. And there's sometimes very good reasons to do that. But if you can, it's often easier to grab something like a command line client provided by a company for integration. Or if they've got a plugin that provides a step, to use that. That's usually going to be cleaner, have better error handling, and perform better in your master. I've seen things like people using curl calls to fetch REST API data, and then using read file to load it on the master, and then calling a parser, and then manually pulling values out of that. And there was a time where that was really the only option. And it worked, but it wasn't really very fast. Because all of that work, aside from the curl call, is happening on the master itself. So just think about it. Each one of these little overheads is adding up to something. So just bear in mind, and I'm going to cite Jesse's talk earlier on how to use Jenkins less. Think about sort of the best way to integrate with something. Sometimes it's just simpler to make a shell call than to try to write some complex pipeline logic. OK, So let's talk specific bottlenecks here. I've put all my caveats up front there. All right, so this is a master that has been brought to its knees. I'll show over here for those people. So this is a graph CPU and I/O per second. This is actually, so this is simulated data, but this is actually mimicking something I saw at one of the world's top 10 companies. This is a huge company. And I've exaggerated a little bit here, but if you look at this graph, it's broken down by different categories of CPU use. And I'll explain this for people who are maybe not as involved in the Linux systems. There's different ways your CPU can be used. It can be running a user program, system activity, that's usually system API calls. It could be just sitting idle, or it could be waiting for I/O. That's often going to be waiting to read something from disk. So this is a master where the wait for I/O is occupying 90% of the CPU. Actually, 94%. So basically, this is a master that's doing nothing but trying to access the disk, and it's completely bogged down doing that. And in fact, if I look at the I/O graph here, in green we have the I/O per second. That's the number of, in this case, write operations per second. You can see it's kind of flatlined at about 50. And that's because this is actually simulating a master doing meaningful work running with a single hard drive, a single physical spinning piece of metal. A single spinning piece of metal where you have to rotate every time you want to write something. It's actually got to move, which means the seek times are low, which means there's only so many times you can write to a different place per second, usually between about 100 and 200 for most hard drives. Now, I mentioned this is something I actually saw at a bigger company. What happened was, middle of the day, their master gets very busy. They've got a lot of teams committing code, lots of build, lots of testing, lots of deployment happening. And it got slower and slower and slower and slower. Eventually, even the UI wouldn't respond. And when we popped up the server, this is more or less what we found. What it turned out was they had this really fancy network filer. They had using it as the volume provider for the master, but physically, it had one single hard drive behind it. One. This is for a big enterprise company. So just bear in mind that for Jenkins, remember I mentioned that it's transactional for running pipelines and to a certain extent for other builds? That I/O matters. All right, I'm going to jump forward here. And I'll show you what happens if you switch from hard drive to SSD. And this is using some simulated I/O limits for that. So this is more or less the same situation. And then this is after I switch to direct access to a fairly fast NVMe SSD. That's one of the faster standards that's got direct PCIe access. So you see that up here we have build times, the yellow dotted line. You see, look, that's pretty high. Look how much that drops. Look at the I/O wait here, the green line. Look how low that is. It's like 1 or 2% from 90%. Flatline I/O, thousands of I/O per second. So my point here is basically hardware matters. We're used to thinking of the impact that software has and thinking in terms of, well, what can I do to make this faster? But sometimes the easiest solution is just to throw metal at it. My recommendation, always run your Jenkins instance on an SSD. It touches a lot of little XML files in the operation. This ensures you can do that transactional behavior and it'll perform nicely. And just to quote some numbers, if I actually do the analysis, I'll jump back here. So you'll see that here the build times are around a minute. Here the build times are around 10 seconds. I have a throttler here that adds 10 seconds to each build so it doesn't loop as fast as it can and just churn through it. So basically the overhead here is about a second with an SSD. It's about 50 seconds with a hard drive. That's a 50 times difference just by changing the hardware behind your system. And SSDs are pretty cheap now. I mean, you can get a very large capacity one for a couple $100. At enterprise scale, that's a no-brainer. Okay, so that's the easy hardware fix. That's kind of the key point. Let me show you some software things you can do. So this is changing pipeline code. So this is a common pattern I've seen in a lot of pipelines. It's very logical if you're someone coming from another programming language. You're going to put some echoes in there, just basically the equivalent of a print line, right? You're going to throw out some formatted content, get a nice little sort of formatted chart, I guess, that shows some information, or use it maybe for debug logging. But the catch is, remember I said this is transactional. Each one of these is writing 4 times to disk with each run. So it's not such a big deal if you're running 4 or 5 of them. But let's imagine you're running this each time you run a unit test, and you've got a parallel that's running 50 branches. Because you're building maybe many different environments, many different kinds of tests, and you want to complete them quickly and get feedback. That adds up. Remember, you've got a limited amount of I/O. So one really super easy thing you can do is just consolidate those steps. It's the same content, you're just echoing out a bigger string. Really simple, but it makes a huge difference in performance. I've seen some pipelines that have 7,000 steps in one case, and 3,500 of those were just echoes. So that's a pipeline that is writing 3,500 times 4 I/O, when it could be writing a fraction of that. That's a really great opportunity for optimization. And that'll reduce your I/O exponentially in practice. It's also a very easy thing to do. And this is what I'm showing you here. This is actually sort of the starting point. There's an even better way to do this, because I'm going to touch on one other point. So remember I said about how you're persisting the program state in memory, basically dumping all of the pipeline variables in memory to disk for durability. Well, writing everything to disk carries a cost. Normally, you're not going to have a ton of stuff floating around there. You'll have a couple of, maybe some strings, a couple of maps, some information about what kinds of parameters you're taking. But one common thing I see is people do some parsing. You know, they need to get some information from a POM file, config file, something like that. That's reasonable. I mean, that's something it's a very common use case. But it becomes a problem if you do it like this. Can anyone identify why that's a problem? Look at the code. Can anyone raise hands? All right, you. Not the credentials, close. Assume that you're running this at the top of your pipeline, so this is followed by a lot of steps after this echo. Yeah, so this read file, you're returning the entire POM file, and that could be a couple of kilobytes, that could be a megabyte. You don't know, right? And if you do this with every single step, think of a 1 megabyte file written with every single step you run. And most pipelines, I estimate, have a couple hundred steps, sometimes up to 1,000 or more. So that's a couple hundred megabytes of writes. That's going to slow down your master a lot, especially if you're running a dozen or more of them. So one really easy way to fix that is just to limit the scope of your variables. Just remember, you need to be able to, don't define globals, right? You don't want to use global variables. You want to use scoped variables, locals. So what this does is factor out that variable. It does the extraction and only returns the little bit that you need. And that means when you persist state, you're only going to persist this little list of strings, which could be very short, rather than that entire POM file. I'm also showing one other little trick here, which is using a shell script to do extraction with return standard out. So this is a good way to offload some of the work from your master. Make your build agents do it. You've got tons of those, right? Those are basically disposable. You can spin up 1,000 instances like that. It costs a little bit of money, but it's a lot cheaper than watching all of your developers see their build slow down. So this is basically using a shell script to do a fetch from the POM file and then just returning the little tiny bit. And the return standard out means that you're bounding it to a variable, and because this is scoped here to only this function, right, it's a local, we're returning just that little split bit here. Makes a huge difference in the amount of data you persist. I've seen some cases where people are literally dumping several megabytes of data with every single step they run. And the result is pipelines can vary, depending on the disk load, between 30 minutes and 2 hours. One little tweak, that's all it takes. Can make that run a fraction of the time. All right, so a couple other things you can do. These are sort of higher level tuning. At the system level, Jenkins uses the temp files a lot, and it does touch the WAR and the plugins. That's the program and the plugins that are installed in your master quite frequently. So there's something in Linux systems called TempFS. What that is a volatile storage. Everything is not written to actual physical disk, it's written to memory. Which is a problem if you run out of memory, but it'll throw things out if you do. But if you mount your WAR, which will be unpacked at startup, and your plugins to TempFS, that means that it'll run a lot faster. All right, I'm going to talk about CPU bottlenecks next. All right, so I mentioned CPS versus non-CPS, or normal pipeline versus non-CPS, the fast mode. So this is fast mode. This is running a merge sort as a proxy for some of the kind of complex logic you often see in pipelines. So I've seen, remember those thousands of lines of code that many shared libraries have and many pipelines have in the enterprise? Which is, it's very legitimate. You have complex business practices. But non-CPS, you see this is running very quickly. In fact, the blue dotted line, I've got the axis over here, is time to complete a build. And this is showing several different phases over time. So you can see this is just over 10 seconds. It's got that little 10-second wait loop here again. This is closer to 15 seconds here. And if we look at this version, it's 25 to 30 seconds. The only difference here, it's exact same code, exact same logic. All I did was throw @non-CPS in the functions here. Here's where I left them off. I'll tell you, one of the users I worked with had a very complex pipeline for the enterprise. They had a lot of stuff that was running as normal pipeline code, doing some complex for loops and filtering and transformation and parsing. I pointed out a couple of small bottlenecks, common functions that were used often. They put @non-CPS on them. They saw a 30% reduction in build time just by putting one line of code in a couple of places. And that's before they even did any other optimization. So this is a very powerful technique. There's a couple of catches. Like I said, you're not getting durability, but usually most of that logic you can just rerun it. So just bear in mind, there are optimization and tuning tricks for your code. Now this one is kind of a special case. I mentioned echo steps and logging. So this is over here. This is when you add an echo step to log a little bit of information with each of those recursive function calls for the merge sort. And you could see the time goes up exponentially. So actually, numbers first. So 10-second wait, 1 second to run. 10-second wait plus about 5 additional seconds, so 15 seconds total. So this is 5 times faster running non-CPS code. And this is even slower when you're adding those echo steps. So think of this as 1 times the runtime, 5 times the runtime, and let's see, 25, 30, so 20 times the runtime total. There's that 10-second wait. So 1, 5, 20. Pretty big difference, right? Yeah. Okay. Have I lost everyone here, or are people still tracking? I know I've jumped through some stuff really quickly. Anyone want me to pause and explain? Okay, cool, excellent. All right, so let's talk about yeah. What if you don't want to, I'm sorry, the question is if non-CP, okay, so the question is, if non-CPS is so much faster, why don't we do it for everything? So I'll give you, so the short answer is because, as you know, that you lose that durability. But the longer answer is there are ways to do that. You could do, for example, mount your job directory as a RAM disk. And then all of those writes are going straight to memory. It might be an interesting feature to look into, though. That's something I could probably add without too much difficulty. But there are some restrictions in how the execution model interacts with the steps that make it a little bit trickier to do that than it would seem. Some of the architecture relies on having a more comprehensive understanding of the program model in order to execute steps. Let's talk after. I can show you a little bit more of the code, and I think that'll make a little bit more sense. All right, so as far as CPU bottlenecks, there's a couple of really easy things you can do. So one is to offload work onto your build agents. They're cheap, they're plentiful, they're basically disposable. Use shell steps to do stuff. Use some external scripts. Remember, you can still write bash scripts and execute them. You can still write Groovy scripts, run programs from the shell. Any of these are good ways to kind of offload some of the work and make it easier to test it in isolation from the full environment of your master. Because you can unit test all of those separate pieces of code. Faster, easier to maintain. Easier to debug, too. Yes? I'm sorry. I should have defined that. CPS stands for continuation passing style. Anytime I say CPS by accident, assume I'm saying normal pipeline code. It's a transformation that ensures that the entire program state is carried around in one object that's passed from function execution to function execution. So it's basically rewriting the program in sort of a functional way. And that's what enables that durability. All right, so offloading work from the master, running functions with non-CPS for stuff that's a little more demanding, using shared libraries, global shared libraries, which don't have those sandboxing checks, which also have some overheads. And all of these are things that can reduce the load in your master and improve your scalability tremendously. All right, so I've talked about bottlenecks. Give me 1 second. 1 second. Next point is scaling out. I use old generation heap as a good metric for when to scale out. And let me explain what that means, and then I'll take your question after this one. In Java, the way the memory is managed, it's split into two spaces, basically, in most implementations. Young generation and old generation. You can think of young generation as working memory, what you're thinking about right now, minute to minute. You got like a checklist in your head, and I'm going to do this, I'm going to do this, I'm going to do this. On the master, that's things like jobs, jobs that are running, whatever current requests are being handled, parsing a file, little one-off things. Also some caching of smaller objects. Old generation is the permanent stuff. That's everything that's continuously happening. Your server config, some of the information about the jobs, users, things that are persistent. That's your proxy for how much your system is essentially permanently doing at once, that needs to stick around. So what I like to say is at the 16 gig of old gen point, and you can measure this using a variety of tools, you need to start to look to scale out. At the 30 gig point, you absolutely should be splitting your masters. And that's not actually because there's a hard limit on Java processes. I was looking at someone's master today, which was running with a 60 gig heap, which about half of which was old gen. And this is more of a management thing. If you have too many things happening in your master, you've put all your eggs in one basket. If it falls over, you're screwed. So that's the point at which you want to start to scale out just for maintainability's sake. I'll also mention it's important for memory use to have enough for operating system caching and metaspace, which is loading Java classes. You want to have enough system memory that's not given to heap to do all of these things. All right, let me take your question now. Mm-hmm. Yeah, so I'm actually going to jump back a couple slides here. I skimmed over something for time. Logging is one of the key things that can cause overheads in your master. So in many cases, reducing log output will have some impact. Usually it's not such a big deal as long as you're not writing megabytes and megabytes of data per build. Like I've sometimes seen large blocks of binary echoed out or very verbose logging. But yeah, I mean, the amount of log data does have an impact. It's not as bad as the number of random I/O because most of that is streamed sequentially, which has better performance. Your operating system can consolidate those into very big block writes, which are much more performant. But just be mindful of the amount of data you're logging. So it's an excellent point. Okay. All right, shoot. Yeah. Oh, excellent question. Okay, so the question is, what if the question about scaling out your masters on the basis of your old gen heap, what if you're running in a container? That's a really good question, actually. In that case, containers are not necessarily, so think of your container as a separate operating system. Whether or not it's running in a container or VM or bare metal, you still have a certain amount of activity in the master. Remember I said the scale out is not necessarily purely for performance reasons, although there are some challenges at scale. It's more for system management. So even if you're running one giant mega Docker container that is given, say, 100 gigs of memory to the heap, that's not that different for these purposes from a master that's running on bare metal. It's just a little bit slower. Yeah. Yeah, so the question is, what he's saying is, basically for the container, you have to allocate memory not just for the JVM, but for the other operating system processes. And that's a really good point. I think that's actually down at the bottom here. You need to allow extra memory. I would say, in fact, something like half of your memory, between 20% and 40% maybe, is a good overhead to allow for things like the metaspace, native buffers for your JVM, operating system caching, and other operating system processes. And that is kind of an extra overhead you incur if you're running containers, because you're allocating that to some extent, not completely, because there is some sharing, and Docker does some nice little magic under the hood. But you do need to pay some of that if you're running containers. A lot of this is actually portable regardless of the environment you're running. This is very system level stuff. GC is another one like that. So GC tuning this is sort of a special pull-out topic. I'm only going to touch on it and say that it's important, and that's because I put together a really long blog post on how to tune Jenkins, and I've got the secret sauce here that's been battle tested at multiple very large enterprises and refined over time, and that delivers very good results for just about everyone I've seen use it. But the difference between tuning your garbage collection, that's the way Java manages its memory and throws out old objects when it's done with it, can be the difference between pauses, when your application is doing almost nothing, of up to several seconds, or in some extreme cases as much as a minute. That's when your Jenkins master is completely unresponsive. It's halted for garbage collection. Versus pauses that are on the order of, say, 50 to 75 milliseconds. You won't even notice. So I recommend using sort of a trusted set of GC settings, because properly tuned garbage collection can make a very big difference, especially for masters using a lot of memory. And I generally recommend, if you're looking to tune it, measure, measure, measure. There's a whole art to this. I could give 2 separate 45-minute talks just on this subject, and I'm not going to, because I don't want to bore you guys to death. All right, important note, these are running from instrumented simulated environments. No real users were harmed in this process, so don't panic. All right, final section. This one's shorter. All right, capacity planning. So I'm going to throw up just a quick table here of what different operations use different resources. I touched on 4 to 5 writes per pipeline step. What I found is that a rough estimate is you can run about 100 pipeline steps, trivial pipeline steps with an echo for every CPU in your system. It's assuming they're not doing anything super demanding. So bear in mind that those do incur an overhead, and logging incurs some extra overhead, as the gentleman over here mentioned. Also, you do need to be, to some extent, mindful of network bandwidth, especially if you're passing gigantic files between your master. So that's like stashing and unstashing in pipeline. That is a remoting channel. That's a finite resource. There's a latency for network calls, and there's a limited amount of network bandwidth. So if you're passing, say, multi-gigabyte binaries, it's going to take you a second or two, right? I'm not going to go through these in depth, but the slides will be available after, so if people want to poke at this and peruse it, they'll be up there. There's a whole variety of different tools here that you can use to look at your memory use and your CPU and your other resources. I recommend for Linux users, and I'm sorry this is Linux biased, I don't really know as much about Windows. I know Perfmon will give you most of these. But VMstat is really helpful. I also recommend using system monitoring tools. I've had very good experiences recently with Telegraph for collecting lightweight metrics. Telegraph and Influx. Jenkins also provides a metrics plugin that gives you some goodies. And the reason that matters is, when talking performance, what you need is numbers. So we can talk about abstracts, this takes this takes that, but those are more theoretical for most people. What matters is how it performs for your system. It doesn't matter, this other guy says, oh, it's fast for me. Who cares? It's not, his system may be doing something completely different from yours. Maybe he's running one quick checkout and just a quick Ruby build or something. Maybe you're building a larger enterprise application and deploying it across 5 environments. So the real way to get good scaling and good capacity planning is to measure. So this is real data from a real user. That's why it's ugly. It's gritty, it's pixelated. This is something that someone had emailed to me when they were trying to analyze a system, and I've anonymized it. But the important thing to do is to look at peak load and load over time. And the reason that matters is because you can say, oh, our average load in the server is, say, 2% CPU. But if you've got a spike at noon when everyone is going in and deciding they're going to push their code and go off and grab a quick lunch, then that's going to put a lot more than 2% load in your master. And this is a very common pattern. So you see this is spiking right around midday. This is CPU use, user CPU use in green, and system in red. And to measure capacity, what I recommend doing is going, okay, here's our total capacity, here's our peak, here's our base minimal load. You want to leave roughly 40% to 50% over your peak plus your base. So it's leaving a nice margin for error. And that's also a good number you can use when you need to onboard more users. You can say we've got, say, 10 dev teams with 10 people on them, so 100 developers pushing code. Well, we want to add a mega team from another company we've acquired with 50 developers. Well, how much do we need to increase our resources? Can we get by with the server we have? This kind of graph will let you do that. Okay, so I said measure, measure, measure. I'm going to break my own rule here. Sorry. If you have to guess, these are some kind of rough estimates for what I would recommend for different size companies and different size teams. Don't hold me to it if your team with 100 people somehow manages to burn up a 20-core master. Like I said, that varies depending on what you're doing, but these are just kind of a good starting point for when you're spinning up infrastructure and systems. Okay, so to sum up, I'm also out of time here. Pipeline is a very powerful tool. It's important to use it effectively. Keep an eye on CPU and especially I/O for your master. Make some effort to tune your pipeline code as well as your system configuration to get the best performance. And by limiting the work in the master, you can run very large teams on Jenkins effectively with a fairly limited amount of resources. And that's it. I've got some further reading. Like I said, the slides will be up here later. And I'm throwing the floor open for questions. Also have a kitten. Just because. All right, questions? Yeah, if anyone wants to take photos, by all means. This also includes another link for the GC tuning talk. Stephen Connolly's talk last year is very applicable if you're not running pipelines, if you're doing freestyle builds, and that talks about the executors and how many you can run concurrently, and that a very limited master can manage a lot of build agents. Question here. Mm-hmm. So the question is, if I have a large master that has a ton of different projects, how do I find out which one is proposing a performance problem? That's a really good question. Actually, one I get asked a lot. And the answer is, one really good way to do it, there's two really good approaches. For I/O, I mentioned that a lot of the I/O comes from the logging and the pipeline flow nodes. One really good thing to do is to go to that workflow directory, look at how many flow nodes there are, how many step records. If you go to the actual build itself and click to the left, there'll be something called steps. You'll get a list of different steps run at the bottom. Look at the bottom one. It'll have an ID when you mouse over it. Maybe it'll be something like 100, maybe it'll be something like 1,000. And that'll tell you roughly how many steps you're running. So that gives you an idea of which builds have a lot of I/O. And you can do this. There's a Groovy script I can hand you that will do this for you. The other thing to do is to track those metrics over time and look for spikes in CPU or disk I/O and correlate those with which builds are running at that given time. Question there. Yes. The Swarm plugin jar? Most of those agents are fairly lightweight. I mean, it depends on what you're. It's more important what you're actually doing with the agent than the fact that you're running like a Swarm jar or something on it. Like those agents, I mean, the Java configuration may give it a lot more memory if you're using default than you actually need, but the actual resource use is very light. Like the majority of it is going to be the build activity taking place on your node. Yeah, you caught me. I'm using Grafana. Unfortunately, the charts come from something that is proprietary to CloudBees that I'm using to do performance testing, but there's a couple of really good products from CloudBees that are used for providing analytics and visualization. CloudBees has an analytics product backed by Elasticsearch that uses Kibana for showing metrics. There's some new stuff that has been announced at this conference, which one component of which is providing performance metrics and visualization. I think that might be up your alley. A lot of this also can be fairly easily baked from constructing a reporter, a metrics reporter, like a Graphite metrics reporter that is coupled to Jenkins metrics plus a system monitoring agent. I can tell you that one was built with InfluxDB plus Grafana plus Telegraph for reporting metrics plus Jenkins metrics plus a little bit of my own secret sauce for a couple of useful things. And hopefully that secret sauce I will be able to open source soon. Sure. Yeah. So the question is, most of the rules here will be applicable to Docker. Is there anything that is entirely specific to Docker? And the answer is yes, but I don't know a lot about the specific performance differences. The storage driver is very important for Docker. That gives you basically container file system performance. The use of the volumes and how you're doing your volume driver can matter a lot. There's also a runtime option for Docker to mount in something like TempFS. And I think for Linux VMs, that can be extremely useful because, as I mentioned, the temp folder is used very heavily by Jenkins. Beyond that, I think that's still something that's being characterized, especially because the Docker project is moving so quickly, and a lot of these performance tuning rules are kind of changing over time. So, yeah, I think the biggest one is to always run the latest version that is stable for you. Sure. All right, other questions? I think I saw another hand over here. Sorry, which slide? Sure, the hardware one, this one. All right, I'll leave that up there for you to take photos of. All right, who else has questions? Did I get them all? All right, excellent.